Hey, thanks. Thanks a lot for this opportunity to participate in this very interesting workshop. So I'm very excited in listening all the speakers' contributions in this very intense week about mathematics of machine learning. And so the plan for my talk today is to introduce some of the ideas that underlie the current activity around the mathematics of machine learning. So as you all know, machine learning is the problem of learning maps, taking inputs that we denote by X and trying to predict outputs that we'll denote by Y. And the idea is to try and find a map that models what we usually observe in various experiments where we want to use a machine to stand in for the human. So we would like to understand a mapping that allows to predict what we're going to see in the future, or the labels of a certain image, for example, or the kind of decision we have to make in the face of events when we use a self-driving car, for example. So we want to predict a map, or we want to estimate a map which has good prediction performance on test data. So this is the problem of machine learning. And around this problem, a lot of mathematical challenges arise. And I will try to describe these challenges and some of the possible avenues that the community is currently exploring, and some of perhaps new results that we can try to think about when we want to address in a simple manner some of these issues. So, so this problem, as I mentioned, is of fundamental significance. It has an amazing number of applications, for example, in image recognition, when you want to predict a category, but it also now pervades the field of engineering in many ways, because people now want to use deep learning for solving hard nonlinear PDEs, for example. And so that makes this field very exciting because of the possible applications that people are now discovering. Another very exciting and impactful application is to understand language and make use of the information we can find in from several sources in order to make decisions. So the problem that mathematicians are facing is the one of coming up with provable guarantees about the estimated mapping. So examples that are extensively used in the literature and the everyday practice of machine learning are, of course, the linear regression classifiers, kernel methods, tree-based methods, non-parametric regressions with nearest neighbors, and the like. And all these techniques have been thoroughly studied. Some of their interesting properties are still to be discovered, but we think we know a lot about this. So deep learning is a kind of technique which finds its roots in the 70s and 80s, where the type of mapping is prescribed to belong to a certain class of mappings consisting of different layers that combine linear, or say affine transformations with nonlinearities applied component-wise. So this is the type of function that we want to study, and which has proved very efficient in many applications. So we'll reduce the study to this very simple class of functions. Of course, now research has made tremendous progress, and different kinds of functions have been used very successfully in many applications, but this is the basic setup. So as we all know, the performance have increased quite a lot in the last years, and say now people are building networks which are more and more stable, and with approximation errors which are smaller and smaller. And the price for this is the increase of the number of parameters. So the success relies on two indispensable factors, which are the availability of huge data sets that are shared across the world, and immense computing power resulting from clusters of graphic processing units. And these resources have only recently been available. So coming with this architecture and with this framework, two problems arise. The first one is that we have to understand overparameterization. So the success of these networks is really based upon the fact that we can use a lot of parameters to model the function. And we all know in statistics and approximation theory that if we have a lot of parameters, we might overfit, which means we're not going to be able to predict anything because we're trying to model the noise rather than the true function underlying the experiment. The other pitfall that we might face when we use such overparameterized architectures is the non-convexity of the estimation problem that is associated to it. So even if we have very large computational capabilities, then we still may not be able to find global minimizers to the loss function we want to minimize in order to estimate the function. So a lot remains to be understood. So why are we overparameterizing? We need to have several layers in order to decompose the information into different scales. And in order to obtain this, we have to introduce a lot of parameters, of course, as a function of the number of layers. So these layers allow to capture different features of the information we want to understand and describe. So this has allowed to arrive at a certain number of successes, like for example, when using GANs, we obtain amazing results at producing new images which look realistic and which may be applicable for certain areas of the industrial world. So why overparameterize? In a few words, depth helps to efficiently extract features from the data set. Also, from a theoretical viewpoint, we know that if we increase depth and width, we'll be able to model these networks as PDEs. And so this will allow us to obtain very interesting results. But a lot of talks in this workshop will address this point of view. So what is the problem with this overparameterization in terms of being able to solve the optimization problem associated with the learning? So the more parameters you have, the more probable many local minimizers will arise with, say, which will not be optimal for prediction. So we'll have to avoid this, and common practice advises to run the stochastic gradient algorithm, for example, and experiences have shown that this usually leads to very good estimators. So we'll have to resolve this, or we'll have to understand why this is actually the case, that we can obtain good mappings, good estimators, while facing so many puzzling properties of the networks. So I will speak quickly of the various features and the kind of research that people are undertaking in order to understand the properties of deep neural networks. So we have 4 items that are usually extensively studied in the community: expressivity, generalization, the properties of the optimization algorithms, and recently interpolation, which is associated with generalization. So I just wanted to say a few words about the approximation capabilities of deep neural networks, because there's been an amazing list of great results around the question of what kind of mappings deep neural networks are able to approximate. So the list is long, but you can extract some of very influential papers by Jarodsky, for example, followed by some of Doboshi's, Devor, Foucault, Hanin, and Petrova, for example, which study the nonlinear approximation analysis of real use, which are specific deep neural networks using a piecewise linear function as an activation nonlinearity. Approximation of functions in Sobolev spaces by Goring, Kutiniok, and Peterson have also been investigated with great success. Recent work by Wayne and E and collaborators have allowed to understand better the approximation spaces associated with deep neural networks, and that they call the Barron spaces. And so they play the same role as Pesov spaces, for example, when explaining the nonlinear approximation properties of wavelet bases and the like. Also, very interesting results on the approximation of analytic maps have been discovered also lately. So one of the nice theorems we're going to use at the end of the talk is the following one by Goering, Kutiniok, and Peterson. And it says that if you have a function, so map from 0, 1, say, power d to r, then if this map belongs to a Sobolev space, WKP, which means that it's going to be k times differentiable with kth derivative belonging to LP, then there exists a vector of weights and an associated neural network which will approximate this function in a fractional Sobolev norm with error less than epsilon. And they control the number of layers and the number of neurons. So this is an amazing result, and it can prove very handy in various situations where you want to understand deep neural networks. So generalization has also been extensively studied, and there is an amazing series of amazing results obtained by Bartlett, Barron, and many others, Rachlin, and I will speak a little bit about this. So just to summarize, people have been studying generalization through the lens of complexities such as Rademacher complexities or Pack-Bayesian theory. And all these results have led to bounds on the generalization error, which depend on the number of layers. And so I will maybe skip over the details, but there's been a series of papers trying to prove that it's possible to have generalization errors which do not depend so much on the number of layers, and more precisely bounds that do not blow up as a function of the number of layers. So there is a very interesting paper by Aurora G, Neishabur, and Zhang, which proves that you can actually approximate a deep neural network with a network with few parameters, and so as a result, very good generalization capabilities. So some very interesting results in this direction use core set, but I will not elaborate on this too much. Some very interesting, very recent results by Golovich, Rachlin, and Shamir prove that the generalization bound does not explode as a function of the number of layers, and it's a very influential paper at the moment. So what about algorithms? So what do people know? So recently people have studied the properties of the stochastic gradient, and they've shown that actually they converge to well, a point in a very small neighborhood of the initialization. So this was an amazing result, proved by many authors in different forums. And so this is a paper by Oimak and Sultan Kotabi from 2018 that proves that so the trajectory is not very long from the initialization to the solution of this stochastic gradient, which motivates the fact that we can study networks, say, by making linear approximations and come up with what we call a tangent kernel network. So we can use techniques, say, from kernels in order to study deep neural networks in a certain regime. However, this comes with certain limitations, and people are not trying to go beyond this tangent kernel limit in order to understand the capabilities of deep neural networks far from the initialization of the stochastic gradient method. So a lot has been done in this area as well. People have proved that the wider the neural networks is, the closer to a linear model under gradient descent it gets. So this is a very interesting result by Soldikenstein and co-authors. I also wanted to add a few words about the importance of flatness. So this is a very important idea that if the minimizer reached by the stochastic gradient, for example, is flat, so if the Hessian is say, close to degenerate, then generalization will be well controlled. And of course, algorithms, so the basin of attraction for these algorithms will be larger, and the chance of reaching them will be larger as well. So flatness seems to be one of the key features that allow algorithms to reach meaningful minimizers. So this is a picture taken from the paper by Goldstein and co-authors that shows that you get a certain robustness with flat minimizers that you lose with steep minimizers. So there is also another direction which I wanted to point. This is a recent work by Lavai and Sujudi, which says that despite the fact that you have plenty of minimizers and sparse minimizers in particular, then using incremental and online algorithms, you can model the trajectories you obtain using a control theoretic perspective that allow that you eventually will avoid the local spurious minimizers. So this is something to explore for deep neural networks as well. What about interpolation? So this is the topic I wanted to say a few words about. So one of the most interesting discoveries lately is the fact that despite the over-parameterization of very successful deep neural networks architectures, you can still say prove generalization bounds that allow to control the efficiency of the network you want to build. And so there's been this very influential paper by Belkin, Su, Ma, Manda in the Proceedings of the National Academy of Science, whose title is Reconciling Modern Machine Learning Practice and the Classical Bias Variance Trade-off. So in this paper, it is advocated that you can use very much over-parameterized networks, and a very interesting double curve phenomenon will occur, which is this. So usually when the number of parameters is less than the sample size, things can go quite well in terms of prediction, and the risk, say, will worsen as the number of parameters approaches the number of observations. And what they were able to observe is the fact that beyond this barrier, the risk will go down again as the number of parameters will increase. So this is called the modern interpolation regime. So a lot of work has been done lately in order to understand this. most of this work has been focusing on the linear model and some of its generalizations. So a very interesting paper in that direction is the one by Hasty, Montanari, Rosset, and Chretien, which proves that in the asymptotic regime, they're able to recover the double descent curve. So saying that as the number of parameters increases, then you can still decrease the risk. And so this was very counterintuitive, but now you have a proof of this, at least in the asymptotic regime. So new work, say from the last 6 months, have been able to prove similar results in the finite sample regime. And I just published a paper with Emmanuel Caron on that topic, which just appeared on arXiv for rich functions. So another approach, say, in order to understand that it's possible to interpolate without contradicting statistical optimality is to study different types of estimators, such as this, for example, Ladaraya-Watson estimator. And the pictures taken from the paper by Tsibakov, Raklin, and Belkin, shown here, make it clear that you can actually, for example, like in this picture, you can interpolate points, but say on average, over the domain where you want to define a function, you will get something which will approximate the true function because it will be close to a smooth function enough, and it will be very spiky in the vicinity of the sample points. So it means that on average, things will go okay, and yet interpolation does not hurt that much because it's so spiky around the sample points that say the locations at which problems may be induced by interpolation is very small. So in probability, when you choose a new point, it will select, so it will lie in an area which is far from the interpolation points, and then the estimator will be good enough. So that's one of the ideas that people want to use in order to understand how interpolation does not preclude generalization. So what I wanted to speak about in the last part of the talk is a new approach, which is simple enough to be described in a few minutes, and which is of interest, I think, for exploring the properties of deep overparameterized networks. So part of this theory is was published in a paper we recently put on arXiv with Emmanuel Caron, and so this what I will present is a simple, say, architecture of proof that helps understanding these properties in a very simple manner. So we start with a mathematical model, which consists of a number of observations xi, yi in order d+1, and we'll assume equation 2, which means that the observations will be a nonlinear function of the inputs plus noise. So in our assumptions, we'll require that the xi's are random, iid, and they'll have some other properties that we'll describe in the next slide. And the errors will be assumed to be sub-Gaussians. So they may be dependent, but the vector of errors is required to be sub-Gaussian. So the goal is to estimate f star based on the observations. And we can restrict this estimation to subsets of a Banach space, for example. So what we want to do in order to be able to generalize is to minimize the theoretical risk, which is the expectation of the loss between y and the prediction f of x. So we want to minimize this as a function of f, and we can make meaningful assumptions about the loss, saying that when you get 0 error, so it means the two components are equal, then you should have loss equals 0, and it should be strictly convex, twice, for example, twice continuously differentiable if we need differentiability, and non-negativity. So this is often replaced with the empirical risk, as you know, where we use the training data instead of taking the expectation, and people usually minimize that risk. So it is also common practice to penalize this risk with sparsity promoting penalties, for example, like for the L1 norm. So we'll assume a certain property which has been extensively used in the literature, which is the separation property, saying that the minimum separation in L2 between 2 points in the data set is at least C, the number of samples, power 1 over nu, where nu is the Hölder exponent, is called the Hölder exponent, or the intrinsic dimension of the data manifold. So this has been studied some years ago, and an example is given by a paper by Matthias Hein and Jean-Yves Audibert, which empirically showed that the intrinsic dimension for the MNIST dataset is less than 20. So this means that, or say this corroborates certain attempts at compressing deep neural networks by saying that the complexity, the intrinsic complexity is not as large as what we think. So the message I want to convey here is that you can actually use a very simple theorem by Neubeggers, which he used for the study of nonlinear PDEs and the Nash-Moser type of results for PDEs. And this theorem can be stated as follows. So you consider 3 Banach spaces, B, J, and K. You assume that B is compactly embedded in J. You then assume that you have a function from B to K, which is continuous with respect to the topologies of J and K. So if you denote by BR the ball around U, for example, for a given U, and if you suppose that you start with a function little f here in B, the idea that so if the problem you want to solve is the one of finding a 0 of the functional f, then the idea of Neubeggers' theorem is very simple. It says if you take the directional derivative of that function in the direction h here, given an h, and if you're able to solve this equation with equality to minus f of f here, okay, and if h, the solution to this equation, lies in a ball around 0 with radius r, okay, then and if this holds for any g in a ball of radius r around f, then it says that you will be able to find a solution, so a 0 of that function big F in the same ball around F, okay? So this is a 0 finding theorem, which is very handy, very powerful, and which can be applied in finite dimensional as well as infinite dimensional settings. Okay, so I recall you want to find a 0 of the function big F. You start from little f, okay? And you solve this equation, which says that the directional derivative of f at g in the direction h is equal to minus f of f. So if you're able to solve this with a little h in the vicinity of 0, so it means that you will be able to find a solution, so a 0 to f, in the vicinity of f. Okay, so it's really a quantitative perturbation result. All right. So using that result and computing the direction derivatives of the risk, here we assume that the loss function will be the L2 loss, then you'll be able to compute all the terms related to, associated to your empirical minimization approach. And you'll come up with this equation that you want to solve as a function of h prime, for example, here. Okay, this is just 3 lines of computation. Okay, just taking derivatives, all right? And now you want to solve this, this equation as a function of h here. Okay, and this should hold for all h prime here, all right? So our main result is this. So if you consider the bump function, and if you split the problem into the problem of first approximating f star in a Sobolev space using the ERM, so the empirical risk minimizer, and if you apply the perturbation result of Neuberger to well, if you apply, say, the result of Göring, Chretien, and Petersen to the result obtained by Neubeggers theorem, then you'll solve, so you'll get a good approximation using a deep neural network based on the ERM of the original map F star. Okay, so the main theorem is that, so if you work in a Sobolev space, no, sorry, so if you work in Banach space, if you assume that you take a bump function, which is rescaled with the factor sigma, okay, if sigma is less than this quantity, which is controlled by the intrinsic dimension of the data, okay, then, so to make a long story short, there exists a stationary point of the empirical risk minimization problem, which lies at a distance distinct to the function f star. Sorry, so I said from the neural network, but it's not the neural network, it's the original function f star here. Okay, so it says that you can perturb the original function you're looking for by no more than this quantity and get a minimizer or get a stationary point of the empirical risk. Okay, and if you apply this and combine it, so if you apply this to the case of a Sobolev space and you combine it with the result of Göring, Chretien, and Petersen, then you will obtain this type of result, which is an approximation in LP of the original function f star using a deep neural network with weights w hat, and you will find this deep neural network in the vicinity of the original function with this order of error, depending on the Sobolev norm of the bump function. The dimension d, the power p, so the index of the norm, the intrinsic dimension. And here is the sub-Gaussian constant of the noise. So all these parameters control the error you're going to make. And using the result by Göring, Chretien, and Petersen, you get a bound on the number of layers and the number of neurons that will be necessary in order to achieve this approximation in this LP norm at the end. Okay, so I won't perhaps enter the proof because I think that the time is now limited. But the proof is very easy. It actually relies on trying to interpolate the noise, actually, using functions in a Sobolev space that you will actually decompose using these bump functions. Okay, and you will obtain a bound in the Banach space on the direction h that enters into the description of Neubeggers theorem. So this bound will depend on the norm of psi, the L1 norm of the error, which is a sub-Gaussian vector. And using classical theorems, we'll have a control over all terms in this expression. So combining this with the theorem by Göring-Coutinho comparison completes the proof. So just a few words about what we've done. So the number of layers may have to increase logarithmically with the number of samples in this setting. The total number of parameters blows up polynomially in the number of samples and exponentially in the dimension of the problem. Okay, but this is not a problem. We say we have a lot of parameters and we'll be able to achieve an error. So we expect this number of parameters to increase with the dimension of the problem and the sample dimension. So this is what we expect. And we arrive at a result which is very simple. So this is in fact a very simple exercise in using quantitative zero finding theorems such as Neubeggers. And this we can leverage in order to prove that we can easily control, say, the number, well, the error as a number of layers and number of parameters. And so there is a nice relationship that links this to the intrinsic dimension of the data. So we can also study local minimizers by studying the Hessian using this sort of technique. And one question that remains that really so that is really crucial, I think, for the sequel and for future advances in the field, maybe the one of studying approximation results in the same spirit as the one by Göring, Coutinho, and Pedersen, by introducing the constraint that the neural network that you want to obtain should be a flat minimizer. So that would explain why you can actually approximate things accurately, but also use stochastic gradient type algorithms in order to reach the approximating network, and with high probabilities. So, but this sort of constraint is not really considered at the moment, and I think it's an ingredient that we should perhaps introduce in the approximation theory of functions from various classes. So, okay, so thanks a lot for listening, and I will be happy to respond to all the questions concerning this talk.